So thank you, and good afternoon, everyone, or noon, and thanks for having me. So as I was introduced, my name is Alon, and I'm from Tel Aviv University, from Yoram Dagan's group. And today I will tell you about some nanowires and even smaller wires that we made, all without e-beam lithography, which is fun. So basically, Jean-Marc this morning gave the entire introduction needed to understand this talk about SrTiO3. So I will go straight to talking about two types of wires that I've made. The first would be two-dimensional nanowires. I will tell how I make them, and I will show some results, transport results on them. And then I will talk about one-dimensional wires, how do we make them, and what are the results. So just a brief reintroduction. So SrTiO and LaAlO, as was mentioned earlier, LaAlO is an insulator with 5.6 electron volts gap, and SrTiO is also an insulator. And only when you grow them epitaxially, one on top of the other, do you get the conducting two-dimensional electron gas. I'm stressing that because the entire method we use to confine the two-dimensional electron gas is not by etching or anything like that, but by depositing an amorphous film on part of the substrate, making it dirty, and then we prevent the growth of crystalline films on top of that specific area. So the first way I did that was to make the nanowires. First, I started with the TiO2 titanium oxide terminated substrate, SrTiO substrate. Then you can do that with regular optical lithography. You can pattern it with some pattern. Then you go to your PLD and deposit at room temperature some amorphous oxide with a thickness we can call H. Do a standard liftoff procedure, and then you have your amorphous pattern over there in green. And here you still have your bare SrTiO substrate. Followed by that deposition, you make another deposition at an angle. And this way, the material comes from here and accumulates both here on the amorphous layer, also here on the amorphous layer, and also here on the clean substrate, but what remains clean is this little area, which is equals to its width is equal to h times the tangents of the angle, and this can be very small because you can control thickness of films very easily, much more easily than you can control lateral dimensions in lithography. So the only thing that remains to do is to deposit the epitaxial LaAlO, which grows epitaxially only here, here, and here, and here. It grows as an amorphous film. So you get conductivity only along this narrow channel. So how does it look like? So this is a top view. It's a scanning electron micrograph. So you can see very easily the amorphous film here and here. And you can also see the dark area in here, which is the channel. The bright line here is just the edge effect of the scanning electron microscope. So basically, the device you can see here is 80 nanometers wide. I could make them as thin as 50 nanometers wide. And this is what I'm going to show next, the results of a 50 nanometers wide nanowire. So when you get a device, usually what you want to do is cool it down. So, and as you do that, you measure the resistance. So I measured the resistance of a 5 microns long device and 50 nanometers wide device. And as you can see, it undergoes the superconducting transition at 100 and something millikelvin regime. But you can easily notice that the transition doesn't end here at zero resistance, even though it seems that the slope is saturating. So we've finished the transition, but not at zero resistance.
Is this a two-terminal measurement?
Yeah, it's a two-terminal measurement, but this value is also gate controlled. So I know for certain it's not only the contact resistance. And in fact, we make a pretty decent contact. So at least at high carrier densities of the 2DEG, the contact resistance is not as high as this, never.
Why do you call it superconducting?
Because it undergoes a superconducting transition. So, okay, so let's wait for the rest of the presentation, and maybe you'll understand my interpretation of this and why I'm still calling it superconducting, even though it doesn't go to zero resistance. So when it's cold, it's time to apply the magnetic field. So you can do that in various orientations. So this is what you get for the perpendicular orientation. This is what you get for the parallel orientation. And what remains is the transverse orientation, where the field is in the plane of the sample and perpendicular to the current. So in all of these orientations, what we generally see is negative magnetoresistance at very low fields with some hysteresis. So the blue curves are sweeping the field up, and the red curves are sweeping the field down. What you see here in the perpendicular orientation is a mixture of quenching of superconductivity, which happens at very low fields, mixed with the magnetic effect that we have. And here, because, as was mentioned earlier by Jean-Marc, quenching of superconductivity at parallel field happens at around 2 Tesla. So the effects don't mix here. What you can see here in this tiny inset is what we did after subtracting this superconducting background from the signal. And we get something which is also negative magnetoresistance with some hysteresis. So let's try to understand what happens in there. Let's try to think like spins in a row placed along this wire. So the low resistance state will correspond to parallel spins. Then we start sweeping up the field, and we get the high resistance state, meaning that we have one spin pointing up and another pointing down. This costs us with some resistance. We keep on sweeping the field past zero. We are still in the same high resistance state. We keep on sweeping the field. Both spins align with the field. We get the low resistance state. Then we start sweeping back at a different value of the magnetic field. This is our hysteresis. We get the flip again, going back to the high resistance state. And once again, when we cross zero, this high resistance state remains. So what is, and then back to the low resistance state. What can we learn from that? So if we look at this spin flip system, then the field in which this entire effect takes place is called the saturation field of the magnetization, and it is proportional to the magnetization itself by some geometrical demagnetization factor. So we measured this as function of temperature at 2 orientations, the perpendicular and the transverse orientations, and the parallel orientation. And you can see that, well, the superconducting background goes away. Here, above TC, it's completely gone. And the effect, the saturation field goes down. The effect becomes narrower and narrower in field. So when we plot this saturation field as function of temperature for the perpendicular orientation and for the parallel orientation, we can see that we get these nice curves, and they both go down to zero at a certain temperature. After we fit these mean fit curves, we can normalize both curves by the value of the saturation field at 0 temperature. So yeah, these are both orientations. And all those dots from both orientations collapse on the same curve and give us the transition temperature of around 950 millikelvin. Now, please note, and this goes back to your question, that this temperature is above our superconducting temperature, which is around 300 millikelvin. So at least my interpretation of this is, and I would like to thank Bina for those tiny dipoles, is that we saw that the magnetism is not uniform in these films. Bina will, maybe we'll talk about it later on this week. And if the magnetism is not uniform, and now we force the current to go through a narrow constriction, we force it to go through those dipoles. So maybe if those dipoles aren't superconducting, this is the reason why we have this remnant resistance after these areas that don't have the dipoles in them undergo the superconducting transition. So this is why I'm saying even though it doesn't go to zero, I still call it a superconducting transition. So with that, I would like to conclude on these wires and move on to the next type. So I would like to move from 2 dimensions to 1 dimension. And to do that, I would like to remind you what we're basically doing when we're moving from 3 dimensions to 2 dimensions in oxide interfaces. We're taking 2 3-dimensional bulk insulators, and at the interface between them, we create a 2-dimensional conductor. So I wanted to play the same game again. Take 2 different 2-dimensional insulators and try to get a 1-dimensional conductor. So this would be one of them. We can call it interface A. It's an insulator. And we can take also interface B, which is also an insulator, and hope to get something like that, a 1-dimensional conductor between them. So where would you find them? So thankfully to nature and oxide interfaces, SrTiO3 already gives that to us. We have unit cell control over thickness, and it was shown by some calculations and some other calculations. These were done by Rosita Pencheva, that the metal to insulator transition is not an abrupt transition. In terms of conductivity, it is, but in terms of the density of states and the band structure, it isn't. So basically, every thickness is a different insulator. So we can take, for example, the 1 monolayer and put it next to a 3 monolayer SrTiO3 and hope to get something interesting in the interface between them. So this is exactly what I did. And yeah, here this corresponds to 1, this corresponds to 3. And well, you have a device, you cool it down, and you measure resistance. So first, we can see already at room temperature that it works. I placed contacts only on the interface, like here and here on both sides that cross the wire. And only between these 2 contacts, I found conductivity. If I put something just here or just here and tried to test the resistance between it and the contacts that do cross the wire, I didn't find any resistance up to down to the smallest distances I could align it with. So the conductivity is only along the wire. And as you cool it down, you can see 3 different regimes. So this can be interpreted as at high temperatures, we have some K-rails freeze out. As was mentioned this morning, SrTiO can be easily doped with certain things like oxygen vacancies and intermixes and many more. So I think that here they just freeze out. Then resistance goes down. This is not surprising. This is reduced scattering by phonos and such. And then there is a very sharp increase in resistance at low temperatures, which can be attributed to depletion of some potential well that we may have created there. So we do have confinement and we do have conductivity. So is there anything quantum about it? So to do that, I started scanning the gate, and I saw this very nice trace of steps as a function of gate voltage. This is something we're all familiar with from quantum point contacts, for example, in the semiconductors from the 80s already. What is different about this plot than the regular quantum point contacts is first that if you see here, the distances here, the steps are over 1, but this one is a single e squared over h and not the 2 e squared over h that we're used to from semiconductors. So this could be related maybe to some removal of spin degeneracy that happens for some reason in these wires, maybe related to the magnetism we know that might be in there. Another thing that you cannot see from this plot that's different is that this plot came from a 4 microns long wire. And 4 microns is quite a long distance for such a ballistic effect.
That was a single wire.
So this is from many wires. The next slide actually is for a single wire, but these were the first results I got.
This is wires in parallel.
Yeah, it is wires in parallel, but their conductance also adds up. So the single squared over h cannot be attributed to the parallel, to them being in parallel.
If the voltage was bigger or smaller, I mean,
Well,
you saw the steps only between 12 and 6. Were there other steps outside this range?
okay, so I did. Actually, I swept a very wide range of gate voltages. And in this device, what I saw was something quite unpleasant. Actually, I don't have the plot here, but it's in the paper. The resistance just jumps to a very high value, and then the trace of the steps repeats itself. So I don't really know why is that happening. It could be charges escaping to some traps in the STO, some nasty business. But actually, the next device I'm going to show is much...
Why do you have the conductance jumping by 1 quantum unit?
So if I have what?
You say you have parallel wires.
Okay, so...
You have many chunks of wires.
Okay, so, well, it could be attributed to one of two things. Maybe only one wire works and the other don't work, and this wire gets repopulated by more and more channels, or the wires are opening one by one. This is also a reasonable scenario because STO has an extremely high dielectric constant, and when dimensions are small, the fields from the gate electrode are not uniform. So if they're adjacent to one another, it could be that they're opening up one by one. These traces that you can see here come from a different device. It's a 1 unit cell, 2 unit cells device, and not 1 unit cell, 3 unit cells like before. But this is a single wire. Here indeed, I see this plateau at 1 e squared over h, which you can see is smeared out nicely by temperature, and the magnetic field doesn't do much to it, at least up to 6 Tesla. And I don't see the second step in here. And there could be many reasons to that, but this is still ongoing work. So I'm not really sure if I can say so much more about it. So with this, I would like to conclude. So if you have any questions or comments, I would be happy to answer them.
We have time for 1 or 2 questions. Okay, well, you have this quantum point contact effect. The quanta is over a very long junction. So how can you explain that? Is it because the de Broglie wavelength there is very large, or
So that's a good question, and we have thought about it for a while. So if we remember, so first thing that we have that might be related to that is also that spin degeneracy. And if we put that spin degeneracy together with a strong spin orbit that we know is present in these systems, so you might have so you have spins propagating in a wire, and you have a very strong spin orbit. So it would cost you a lot of energy to scatter back. So that might be the mechanism for that. This is what we're thinking. I did see these quantized steps at lengths of 1 micron, 4 microns, and after that I tried something very ambitious like 40, and I saw steps but not quantized. So it does disappear sometime.
Okay.
Yeah.
One more question here.
Yeah, I mean, I'm really puzzled by only one e squared over h, but it's step 3. So based on what we heard in the morning, how do you explain what can split? It's not. Can it be a spin splitting? Why?
It's not split. You don't see 2 pins. You don't see 2 steps. You see only 1.
That's what.
No, it's said it. It's a removal of
No, but the step
Yeah.
size. The step size.
And if it was spin split, you should see 2 steps.
No.
Yeah.
Should, okay.
Well, at a certain gate voltage.
No. I mean, this is many parallel. But
So
single device, you see single step, right?
yeah, so I saw a single step, but what is also different here than in semiconductors usually you make the gate voltage corresponds to the width of the, if you're using a plunger gate from the side, like a side gates, then you're actually making the device smaller. Here you're increasing the chemical potential with the gate. So, and you'll not promise that the level spacing of the first two levels is the same as, let's say, the second and the third. So, as you can see, I'm barely here on in the temperature range of seeing the first step. And potential wells tend to have their level spacing decrease as you go up in energy. So I think if I would go down to lower temperature, I could see another one, because I really believe I'm populating a quantum well here, and not just making it narrow well.
So what is your ballistic mean free path compared to the length of your channels?
To the length of what?
Your channels.
So I can only know, I mean, I can only put bounds on that, because I have my wire length. The longest one was 4 microns, so that's the upper bound I can give you. If I go very systematically increase it, then I will know the cutoff. But
your mobility is of the order of thousands.
Yeah.
You get condensation in point contacts that have a length of half a micron at most. What you need is mobility of 1 million. And
Yeah.
you don't see any condensation.
So this is why we believe this spin orbit plus spin polarization effect
Why
helps
can't
us.
there just be some resonant tunneling through impurities? I mean, you always get that if you squeeze another wire.
Well, so here I didn't see any change of this in this plateau up to 6 Tesla. So if you had something like that, you would expect to see some interference.
Okay, I think we should stop here because we're already over time. Thank you. Okay, the last presentation